Well, let's see. Almost. Oh yes, thank you very much.
Okay.
So, over to you to talk last presentation, management data in computational edge clouds.
Yes.
Thank you very much.
Thank you.
Minutes.
Thank you. So yeah, my name is Jussi Kangasharju. I'm presenting this for my student Nitinder, who couldn't get a visa in time, so he's still waiting in Helsinki and might not be coming here this week. But anyway, so on the motivation, I'm going to go a little bit quicker here since we've seen this. So edge clouds, what they are, why you want them. So these kinds of small scale servers deployed at the edge for faster computation. So for the benefits of decreasing latency, decreasing network traffic, and also in some cases that when you are computing data that is only of local relevance, so there's no point in transmitting that to a faraway central cloud for processing. And one example, we've been working together with Bosch, so there are already robots like the Bosch APAS that already work alongside humans and need to have these time-critical access so that they don't actually turn in the wrong direction and injure the human that's next to them. And also augmented reality applications with IoT sensor data and all these. So these are already becoming reality in the industry. And we had a paper last year where we sort of extended the term edge has a, if you read the papers on edge computing, try to find what the definition is, you're going to find a multitude of definitions. So we tried to come up with our own, and you see also the term fog computing, which apparently, according to some people at Cisco, is just a marketing term for what everybody else calls edge computing. But we separate, so the key part here is that we kind of identify that there are two types of devices near the edge. So there are these more managed, more dedicated type of devices that we call the fog layer. And then you have these smaller devices that could be even cell phones, in some definitions, sort of voluntary devices that are close to the users, might have a little bit uncertain network connectivity. But you have these two layers, and these are the two things that we play with. Now on this data management, of course the applications, sensors, they're running at the very far end. They need data. We have this data store that we assume to be there, kind of the traditional central cloud for us. That's just a data store. It doesn't do any computations, but we assume all the data is available there. And but for the edge devices to do anything, they need the data. And if the data is available in the data store, so every requests have to go to the data store, then they come back, then you can do the computation what you might need to do there. And obviously, if you do this all the time, then what's the benefit of doing it at the edge, because you need the round trip time to the central data store to get any data. So therefore, there wouldn't be any benefit to having an edge cloud in that case. So the question is, so how would you decide what to cache at the edge so that you'd get the maximal benefits? And the main contribution of our paper is that we propose this kind of an edge cloud caching mechanism where we group these resources at the edge based on what data do they need. I'll explain how this goes. We'll try to sort of do this classification by predicting what data might be required at which resource, and we have a simple mechanism where we try to ensure some kind of a reasonable consistency over these multiple copies of data that exist within this group. So for this cache grouping, we have a three-step iterative algorithm. So we start off with this task deployment, then we get the data in the caches, we do the grouping, and then when there are new tasks, we then again run the task deployment, all this. So the grouping there serves as the tuning knob for the whole system. And here, in the initial step, in the initial task deployment, so you have a task that you need to compute that needs a certain set of resources. And you have a bunch of algorithms, one that we also proposed last year, a bunch of others are possible, but you need a way of saying that this task gets these following resources. Whether they are at the edge or the fog, doesn't matter. And you can deploy multiple tasks. So here it's task 1, the sort of brownish blob, and then the task 2, which is sort of this bluish greenish blob on the right side. So there are 2 tasks that are running that have been allocated these resources there. So in the next phase, these resources, they know that we are computing this and this task. They get the required data for that task. They get it from the central data store, and then they do whatever computation they need to do. And now comes the grouping part. So of course there are multiple tasks. Many of them might be similar in that they sort of like you have a robot that's producing cases for a mobile phone and another robot producing cases for a laptop. So there's a lot of similarity between the two tasks. And in the paper we list a whole bunch of different possible metrics that you could use to group these things. But the key thing here is that we take a set of similar tasks, whatever definition of similarity you use, and these form what we call a workload. And then the system has multiple different kinds of workloads, and all the resources that handle the task of a given workload are this kind of a cache group, and that's the sort of entity where we want to manage the content. So as an example, the task deployment algorithm, so suppose there's a new task T3 here that is similar to workload 2. So therefore, the task deployment algorithm primarily tries to allocate these tasks to the workloads where they belong. Now, of course, maybe the resources aren't enough, they're not suitable for that particular task, but it's still part of that workload. So these workloads and these cache groups, they live, they might expand, maybe even contract. And so you end up with these larger workloads, cache groups. And as you can see in the middle, we don't restrict. One resource could be part of multiple cache groups. However, as I'll show in the results, you don't actually want that to happen. And there is a very good reason, but I'll explain why that you don't want that. The communication is pretty simple. We try to kind of make it simple in the sense that not too much traffic, and try to maintain some reasonable degree of consistency, so that when there are multiple copies of a data item, that you'd always compute on the latest copy. So these different roles that we then assign, so within a cache group, most of the nodes are just group members, and they only have data that belongs to that cache group. Then there's, for every group, there's a group leader that's elected by a distributed election algorithm that is responsible for maintaining the data in that group. And obviously we assume that group leader should have some decent connectivity to all the other group members. The group members don't necessarily need to be able to talk to each other. And we follow a simple pull-based model. So basically sort of asking for data when you need it. We assume also that uploading, whenever there's updated data, it's automatically uploaded into the data store in parallel to all the other computations. So hopefully the data store will always have the goal is that the data store always has an up-to-date copy of any data item. And just for simplicity, we assume that the data store will be there and messages are not lost, but of course in reality you might want to tweak that. For the data structures that we use, so each group member, all it needs to know is that I have this data item, who's my group leader? And that's it. The tag is just is it free or is it locked? The group leader keeps a table where for every data item it keeps track of who was the last member of the group to update the data. So who is the member in the group that has the latest copy? So in addition, of course, to the data store, but if it's in the group, then it's much faster to get it from there. And the data store keeps track of which data is being handled by which group, so keeps these group leader addresses. And also you can have this additional tag for what kind of classifiers, why are these items grouped together. So just to show the content flow, so we have two resources, two nodes, a leader and a data store. So if resource 2 wants to get content X, asks the leader checks from its content table, okay, resource 1 was the last one to, resource 1 was the last one to update it, so then resource 2 asks resource 1 for the newest copy of content X. And it's happy and will continue processing. And then you can see there resource 2 marks the content as being up to date. If there's a failure, if resource 1 for some reason is not available when resource 2 asks for the item X, then after a timeout, resource 2 will realize this is not working, and then you can get the up-to-date content from the data store. So the price you pay here is the timeout and the extra round trip time, but at least you get the data. So what if somebody's working on the data item when you want to get it? So resource 2 asks the leader for content X that is currently being worked on by resource 1. The leader will tell, okay, resource 1 is working on it, but it's currently locked. So then resource 2 will wait for some interval. In this case, in this example, we are lucky enough that resource 1 stops processing before the timeout, and then content becomes free. And when resource 2 again asks, where can I get content X, go to resource 1 and so on. Of course, you might need to wait if the content is being updated further. And then finally, the update. So when resource 2 updates the content, so it has gotten the content, does the update, does whatever processing it needs. So it tells the leader, I want to lock this for updating. It then becomes locked, content is processed, and then resource 2 tells the leader, okay, now it's been completed, and updates the data store. So now after this, of course, any other member in the group who needs content X, the leader would have an information saying it's resource 2 that now has the up-to-date content, so all the requests would go there. So we try to sort of match the requirements, so reducing the unnecessary traffic. Of course, you could always debate whether you should do pull or push, which way is better. We've decided to go with a pull model and provide a simple causal consistency on the data. So on the assumption that no major disasters happen with the resources. And then on the evaluation, so why do we want to do this grouping? Why is this beneficial? So we use the Icarus simulator. Those of you are familiar with it, you know it's an ICN simulator. We're not doing ICN here. We're just using it because it has all the caching stuff built in, so we don't have to try to build our own simulator. And we had a set of fog nodes, edge nodes. All the fog nodes were the group leaders. Some number of content items that we divided in up to 32 different workloads, and different kinds of cache capacities of up to 10% of the overall content catalog size. And the questions that we asked in the evaluation, the first one was, does this grouping bring any benefits? And if yes, what would be the size of the group that you'd want to have? And on the first question, so if here on the x-axis is the cache size as a fraction, y-axis is the hit rate, and two different curves, the blue and the red curves. For blue is for 4 workloads with grouping or no grouping. The red one is for 32 different workloads, same thing. And you see there's an up to 50% increase in the hit rate for when you do grouping. And likewise for latency, you get the same thing. You see about up to 45% decrease in latency for when you do the grouping. And now, why I said that you don't want a resource to be a member of multiple groups, we asked the second question. So if grouping is beneficial, how should you form your groups? And here we defined different numbers of workloads, so 4, 8, 16, 32 workloads as shown by the different colors. And on the x-axis in these two figures we just divided it into an arbitrary number of groups. And what you can see is that you get the maximum gains when the number of groups is equal to the number of workloads. And when you think about it, it's reasonably intuitive in the sense that when each workload, each workload focuses on different items, and all the tasks within a workload work on similar items. And this way, you don't get any mixing between these two different sets of content when they are separate. And at the same time, you may ask, so what if I had a more than? So you have an intuitive case why you want at least as many groups as workloads. And the other point why you don't want any more work groups than workloads is then that at that point, when you start splitting the task of a workload into multiple groups, then you lose some of the caching benefits there. But in conclusion then, so we propose this edge resource grouping strategy to manage content, where we classify the content based on the workloads and the kind of content that the task might need. We have this three-step iterative algorithm to map tasks onto the resources, map content on the caches, and then continue on this cycle. And we've shown that, yes, it makes sense, and that you'd want to have the number of cache groups and the workloads to be similar. And of course, in the future, you can start working on things like how would you then, for example, do these classifications? How would you define, measure the similarity? How would you assign them? All those kinds of things could be part of the future work. And that's the end of my talk. Thank you for your attention. I'll try to answer the questions as best as I can, but there's Nitinder's address. He's also apparently also watching on the live stream. So you can also send questions to him. He might be able to answer better, especially when he goes into lower level details, but high level stuff I can take as well.
Yeah,
so thank you.
Thank you very much. Okay, we have time for just one or two questions. Yes, please, over to you.
Hi, I'm from UCLA. I'm sitting here on these students. So I have a question regarding how your scheme can solve races, because there might be different groups who want to update monitor, because then you are locking and then you're updating. Because if there are so many requests coming.
So you mean multiple different groups working on the same data item?
Right.
So
because it may create the races in the
yeah, it could create, yeah, so if you have same data items that are being updated by multiple groups, then you definitely can end up in a race condition at the data store. But in that case, the solution would need to be, the task deployment algorithms and such, they should end up doing so that all the tasks that need to work on the same data item should be in the same group. So that's the way to avoid the race condition there.
Thank you very much. I'm just interested to see that you pointed out that the workload, because the workload number is the same as the group size you get are an optimum.
Yeah.
It begs the question, there must be some sort of maybe proof that could show that that's true. Is that something you're looking into? Do you think there's an underlying, there seems some intuitive.
It is intuitive when you think about it. I mean, we didn't expect it in advance, but when I saw the results, started thinking about it, why this happened, it sort of was pretty obvious, makes sense. No, we haven't thought about looking into a mathematical proof. You probably could do it.
Yeah. For a PhD student might be interesting.
Yeah, but Nitinder is not that much into math, so.
Fair enough, okay. Well,
apologies, Nitinder.
Yeah, well, I'll do that, yes. One last question.
Yeah.
Question from actually, in physical layer, we can utilize multicast.
Yeah.
So multicast, actually, we can broadcast. Suppose there are more than one request from different group, then one access point may broadcast.
Yeah, that's also true, yeah.
Yeah. Right, I think we'll close it there as we're running out of time. We've gone past time. Thank you very much.
Thank you.